But there are a lot of reasons why that doesn't actually work as a completely closed loop. And the reason is, one of the reasons is we often do a pretty crappy job initially estimating how much it costs. So it ends up costing a lot more than we thought. So we decide we're going to build, we decide on some science, and then we design something that does that science, then we find out it costs more than we thought it was going to cost. Then we have to descope. Then we descope the science, then we come back, and it's a kind of a spiral, and eventually, hopefully, it converges. And of course, LSST, which was developed, the idea for LSST was developed over a period of about 15 years. It's not surprising that some of these arguments are a bit hand-waving. So when you write a proposal to get a project funded, normally the way you write the proposal is say, this is the science that's really crucial, and then it leads, tautologically to the design parameters you've chosen, and that, of course, is a lie. And you'll recognize that as we go through this, because, exactly how deep in the sky do you need to go? We'll discuss some of those things, but or what resolution you need, et cetera. So just some starting points on LSST. I think most of you probably know this, that this survey is extremely powerful. We'll cover the entire southern sky with frequent visits, and there's a very wide range of science that one could imagine doing with such data. And although a lot of us have thought about this for a while now, I'm sure we haven't thought of even 10% of the science that actually will get done with LSST. Most of the science that will get done is stuff we haven't thought of. But you still have to adopt some concrete things to kind of benchmark what you think you need to do, because there are real decisions to be made. And these were the 4 that were chosen. So probing dark energy and dark matter, which all of you are now expert in because you've been listening to the morning's lectures and you're attending the Dark Energy Collaboration meeting. Taking an inventory of the solar system, exploring the transient optical sky, mapping the Milky Way galaxy. And I have some slides later on what this means and why maybe it gives you some requirements. An important point to make is, it's not that the choice of these 4 topics is because those are the most pressing topics in astronomy. We chose these 4 topics because they actually probe the system in different ways. And maybe that's actually worth discussing before I go to some of the slides. What sort of complementary requirements do you think these different topics place on the system? Cadence. So how would the cadence be affected by each of these 4? What would you want in cadence for transient surveys? What characteristics of the cadence would you want for a transient survey? Well, obviously, you want a lot of visits of every part of the sky. But how would what sort of choices would you make about how those visits should be distributed in time? Let's just take a simple case. Suppose you're looking for periodic variable stars, and you want to sample all the periodic variable stars. Should your cadence be, so as we'll show, we'll go through 1,000 visits. Would you make those 1,000 visits evenly sampled in time? Why not? If you think about it, so if you don't know exactly what you're looking for, if you know you're looking for, a 10-day periodic variable, then yeah, you could make a time series that samples it. But if you're looking for periodic variables on timescales from hours to years, you need to have enough power in the window function, if you like, in order to have some responsiveness to all those cycles. So actually, this hasn't been completely worked out yet. Still kind of an open question, but that's an example of where, say, for transient science, you might want to ensure that you have even, a uniform distribution of intervisit times, right? You have some intervisit times which are of order hours and some which are order years, et cetera, so you get power on all those scales. What about for the solar system? What do you think you need for the solar system? Yeah, we'll come to that. I'm just talking about cadence, actually. With cadence, what would be the issues on cadence for solar system surveys? Well, okay, so if you're looking for small bodies, most of them live in the ecliptic plane, so you obviously want to cover the ecliptic plane. That's a good comment. But what about the time sampling? So very fast-moving objects are going to put some constraints on the exposure duration for trailing. And but let's take a different issue. Suppose you actually we didn't design LSST this way, but suppose you only got an observation of each part of the sky once every 10 days or so. Do you think that would cause any problem for detection of moving bodies? Yeah, how would you? I get a point here and a point here. How do I even know it's the same object? Then it becomes a massive data analysis problem to figure out how you would connect all those different points with Keplerian orbits.
Something that was very far out that didn't move very much.
So yes, as we go to the more distant objects, you know, the Kuiper belt, et cetera, then they don't move so fast, so that's an easier.
Isn't that the same kind of argument that we did for transit?
So yes, what it says is that this isn't a single thing, but at the very least, you need relatively closely spaced observations to know that so that you can see an object has moved from here to here, and I know it's very likely the same object, and I get a vector for it, and then you can trace orbits that way.
Spaced in time and on the sky.
Spaced in time and on the sky. So in fact, what was adopted here is that we get back to the same part of the sky within an hour, typically. So there's actually, as you may know for LSST, what we call a visit is actually 2 exposures that are separated by a short interval. But we talk about pairs of visits for the solar system just so that you can see that something's moved from here to here and you get a vector for it, and that helps with the reconstruction. What about mapping the Milky Way? Are there any cadence constraints on mapping the Milky Way? So one of the things you do, the hardest thing, of course, with any kind of galactic science is figuring out how far away things are. And if you want to figure out how far away they are, you're going to use 2 clues. One is parallax and the other is proper motion. And obviously, you need a long enough baseline to get the proper motion vector. So in fact, what it turns out is the proper motion constraints actually depend very strongly on time. Most of the proper motion information we get comes late in the survey, because you want that baseline to see it. And for the parallax, everybody know what parallax is? Yeah. For the parallax, then obviously it's an annual cycle, and you have to have enough spacings or enough phases with respect to the annual cycle to see the stellar wobbles. So anyway, that just shows you ways in which these things, for the cadence, which was the first thing mentioned, might drive the system in different ways. Are there other things that you can imagine that each of these things might drive the system in a particular way? Let's take the easy one, dark energy and dark matter. What's that going to be most sensitive to? What do you think is the single most important quality of LSST that's going to govern our ability to do weak lensing? What? Pixel scale we'll come to later, actually. You don't have a lot of freedom with that. So we'll come to this. So that's number of objects, et cetera. But PSF, yeah. If the PSF for LSST were 1.5 to 2 arc seconds, we don't do weak lensing. So it's very, very sensitive to what the width is, and obviously the systematics of it. And so that's driving image quality, understanding of image quality, how it behaves on time and position, et cetera. Some of that is driven by the solar system as well, because you're trying to construct orbits. And as you imagine, if you're connecting these various points, if you're a little bit off on somewhere, you're going to diverge on the orbits. And mapping the Milky Way, how far out you go depends on the precision we can do proper motion and parallax. And so that drives that as well, but in somewhat different ways. But one of the things that's interesting about this is that, and people said this, that they all depend on surveying a lot of sky. And I won't even ask this because I'm sure you've heard it many times. The rate at which you can survey the sky is given by what we call the étendue, which is the product of the collecting area of the telescope and the field of view of the camera. Can you come up with a very simple argument as to why that's the rate at which you can survey the sky? So there's a very trivial argument. One line. Photons, yes. How many photons do you collect per unit time? That's how big is your mirror and how much of the sky are you covering, right? So obviously it's the product of those two that determines that. And that's the étendue. There's various other ways to phrase it, but basically that's how much light you're collecting, and how much light you're collecting governs how fast you can do that. So LSST has a étendue of 300 meters squared, degrees squared roughly, which is about a factor of 10 higher than any previous facility. The étendue of the Dark Energy Survey telescope is about 30. And then the ultimate science you can do is really integrated étendue, which is étendue times time, because étendue is the rate at which you're collecting photons. So étendue times time is the total number of photons we collect with LSST over the mission. It's kind of like the integrated luminosity for a particle physics experiment, right? Those are your particle physics experimentalists. Okay, so there's a bunch of different kinds of things that you might care about with a telescope, and this is a list of them here. Some of them are pretty obvious. You know, how deep do you go in a single visit? If you're trying to do timing, you know, what's the faintest object I can detect in a single visit? Image quality, which is PSF width, we've already talked about. How accurately do I measure the brightness of an object, either in time or by comparison between two different filter bands, if I'm kind of going to try to get a color, for example, photometric redshift out of it. Astrometric accuracy, how accurately can I tell where a given star or galaxy was relative to background objects, which is obviously connected to motion and things like parallax. The exposure time is related to the depth of a single visit, but it has some other characteristics in terms of short time scale behavior. Obviously, what colors are you measuring? We touched on this, how the distribution of revisit times occurs. How do we sample those 1,000 different visits during the 10 years of observation? This is related to the total number of visits in a given part of the sky. So how are they sampled, and what is the number that you have? If you add together all those different exposures, what's the co-added survey depth? The distribution of visits on the sky, total sky coverage, how you distribute those visits with filter, and then a whole bunch of stuff related to how we process the data and get it out there, which can affect science. For example, and we'll come to this later, if you want to do time domain astronomy, a lot of that is going to be related to, something interesting happened, can I look at it with another telescope? Do we get you the information fast enough that you have time to actually respond in that way? So these are some slides which actually go through a lot of what we've already talked about, you know, looking at each of the four observations, each of these four main science areas for LSST. So probing dark energy and dark matter, you're all familiar with the main techniques: weak lensing, baryon acoustic oscillations, type 1a supernovae, and strong gravitational lensing. And these are quite independent techniques. As you've heard, they depend differently on systematic issues. They depend differently on nuisance cosmological parameters. So it's very valuable for the survey to be doing all of them with the same data. But if you think about this list and how they drive the constraints on the system, it's mostly weak lensing and type 1a. And the reason is that large-scale structure stuff, baryon acoustic oscillations, really just involves measuring the positions of galaxies and their redshifts, whereas weak lensing depends on measuring the shape, and clearly measuring the shape is harder in terms of systematics or system parameters than measuring the centroid or the position. Type 1a is novel within dark energy and dark matter because it's a time domain measurement, and it depends very sensitively on how well we can calibrate the system, et cetera. So these are the two main constraints. Weak lensing, and this was already said, requires deep, wide area multicolor imaging. Multicolor to get photometric redshifts, wide area to get as many objects as possible. Actually, this is something you maybe already did. Is it better for weak lensing to do a survey which is wide and shallow or narrow field and deep? Not a cluster, just the field galaxies I'm going to do cosmic shear with. Which way? I mean, if you got, the Yeton-Du argument tells you that you can either cover a lot of sky shallow in the same amount of time, or you can cover a small amount of sky deeper.
Why then shallow?
Why?
Because there's an intrinsic galaxy shape. There's a galaxy shape measurement error that you can't beat down, but you can a priori. But if you have many galaxies, you can divide it by root n,
Right.
increasing your shape measurement.
So which way gives you more galaxies?
Having a shallow observation, but very wide field of view.
And can you give a simple argument for the others as to why that's true?
For what, sorry?
A simple argument for the others as to why that's true?
Oh, sorry. I guess there's galaxy shape measurement error.
No, aside from that, just the number of galaxies.
Oh, because the more galaxies that you measure, presumably the better that you measure.
No. Why is it more galaxies to go wide and shallow than deep and narrow?
Well, I guess because if you've got a wide field of view, presumably you're seeing more things, right?
Well, if I go deeper, I'm seeing more things too.
But they're fainter. They're fainter, and you might not necessarily measure the shapes that well.
You can write an equation down and work this out. How does the number of galaxies depend on how faint they are, on their intensity? Well, it goes up as the intensity goes down. By how much? What is the relationship? Well, okay. So it's essentially, forget about cosmology, just for a sort of isotropic homogeneous universe, since the light goes down like 1 over r squared, the volume increases like r cubed, the number of objects goes like the intensity of the -3 halves. So going deeper gives you the intensity -3 halves. If you work out the time, okay, how am I going to use my observing time to get that much fainter by sitting on that part of the sky that's preventing me from going shallower? You work this out, you'll find out it's better to go wide and shallow. You just simply get more objects. Now, there are other subtleties associated with sampling different cosmic scales, et cetera, and that's a slightly more complicated argument, although not much more complicated. I mean, when
It's
the
also the floor of the size of the PSF.
right,
When you go to higher redshift galaxies, they start to get smaller than the ground-based telescope's PSF.
right, I actually have that on the slide later.
The important counter-argument is that the lensing signal increases with increasing
That's right. That's right. So it turns out you can make these simple arguments, but you still have to do the correct calculation. And the correct calculation shows it's actually better to go wider and shallow. For a given use of observing time, a given use of Yeton-Du, you're better off going wide and shallow. So,
If I can suggest one great exercise, there is a floor on
Yeah.
both sides,
right,
including on the shallow side.
yeah.
You can figure out how shallow do you want to go. Suppose you have more than 4 Pi radians of the sky. You wouldn't go shallow.
Right. Well, I was just saying, for counting the number of galaxies for weak lensing, just for that particular problem.
I mean, if you were most interested in measuring the Hubble expansion rate at redshift 3, then that's,
Yeah, Yeah, certainly. And that's why I said it also depends on what scales you're measuring, right? So as you go wider part of the field, you're measuring larger angular scales, but in co-moving distance, if you're going shallow, it's not so obvious. You need to work these things out. But people have worked it out, and the answer is wide and shallow is better, within limits, as Boov has said. So a weak lensing survey wants, you want to go as deep as you can, as wide area as you can, and multicolor. You're very sensitive to image quality because the characteristic sizes of galaxies are like an arc-second or so, so it's comparable to what the atmosphere is doing, which means any degradation in the image quality is going to hit you quickly. You need to do, for the redshift determination, you need to have really good photometry in at least 5 of the bands to characterize galaxy colors. Yeah.
I was wondering why we don't have, say, twice as many filters as we have now. Is it that determining the photo Z doesn't get that much better once you have more than 5? Or?
Yeah, so there's an issue about, well, first off, you've got this étendue you're using up. You have more filters, you're spending less time in each filter, which means you're not going as deep in each filter. So it can hit you that way. If the filters are too broad, then your redshift, your ability to determine redshift goes down. So yeah, those considerations compete against each other, and 6 is about the right number, is a way of putting it.
Is there not also an argument that if you just make them shallower and shallower, you're just throwing away photons?
Well, that's the point. You're not using your time efficiently, so the survey is getting much shallower. Yeah. And then this is a big one that we had arguments about early on about do we need short exposures or long exposures. What's unique about LSST, of course, is we do these short exposures and do many of them. And other surveys haven't done that. And people have argued that, well, you're only doing that for asteroids, or you're only doing that for the time domain. Cosmology is a static universe. You don't need that. You could spend all of your observing time in one visit. And the problem, of course, has to do with systematics. If you're doing many, many different exposures, then the telescope's in different configurations, the galaxy's appearing all over the focal plane, the weather conditions are different, the seeing conditions are different. So if you're concerned about how those kinds of effects might yield subtle biases in the determination of shapes of galaxies, then clearly you want the central limit theorem to be your friend. You want as many observations as you can because those things will beat down by like the square root of the number of observations. It's a pretty crude argument, but it clearly goes in that direction. So then there's an issue of, how much sky can you cover and how deep do you have to go? With these numbers, which are characteristic of LSST, we get about 4 million galaxies, which is adequate for stage 4 dark energy constraints. But let me just show this slide before moving on. So this is the point that Boov was making, effectively. So this is the number of galaxies, the angular space density of galaxies, number of galaxies per square arc minute as a function of magnitude. It's what? 4 billion. Did I say 4 million? 4 billion. That should be a B. That should be a B. See, I did that to test you guys, right? That was my exercise. Yeah, 4 billion. So if you plot all galaxies, it's this red line. If you take ones which are not highly elliptical, not edge-on or something, it rolls over a little bit. If you avoid overlaps, et cetera. And these black lines, these are integral curves. These black lines are, the value of f there corresponds to, you only use galaxies that are that factor bigger than your point spread function. And this calculation was done for what were Subaru data. It's an old plot where the seeing was 0.7 arc seconds. So this curve is saying you only use galaxies which are bigger than 1.1 times 0.7 arc seconds, or 1.2, 1.3, 1.4. So that depends on how confident you are in your shape estimation algorithm, given that you're barely resolving the galaxy. But the main point to see in these curves is it doesn't really matter where the level is. They all level off at about 26, 27. So there's no point going fainter because the galaxies overlap. This is the point Booth was making. That there's a limit to how faint you can go from the ground, unless you can do something to dramatically improve the angular resolution, and you're not going to do much better than that. You can do better in space, of course. In space, where you don't have the atmosphere, so this might go down to 0.1 arc second. You can maybe get up to 100 or more galaxies. But obviously in space, you're going to have a much smaller mirror, so your ability to go as faint is going to take a lot longer, et cetera. But for a ground-based project, there's no point in going much beyond RF 27.5. And if you're going to get to RF 27.5, you want to do that because of the argument we made earlier about wide and shallow is better than narrow and deep. You're going to want to do that over as much sky as you can possibly do from a single point in the ground, which is basically half the sky. So LSST is designed to do half the sky down to the limit where galaxies start blending with one another and they're not really that useful anymore. And that turns out to be compatible with the design, was one of the drivers. Okay, the other big piece of dark energy science that affects the design are the type 1a supernovae, because here this is time domain. We require light curves sampled in multiple bands every few days over the course of a few months. One of the things we said with LSST is that we'd get so many supernovae that we could check the Hubble law in different parts of the sky. So we want these supernovae to be distributed all over the sky so we can look in different directions. We want to get out to redshifts where we're going to see supernovae before they get redshifted out of the visible band. That turns out to be about RF 24. So this gives us single visit depth that doesn't really show up in weak lensing. We need good image quality because the supernovae live in galaxies, and you need to separate, for accurate photometry, you need to separate out the supernova light from the galaxy light. We need very good calibration, so we get good redshifts, as well as we do the absolute photometry for the supernovae. And some of this redshift determination could be improved by coupling the LSST observations to infrared bands, which has given rise to some of this discussion we've been having lately about cooperation between WFIRST and LSST, or Euclid and LSST.
I think I've heard some of the supernova people complain they'd like an even shorter exposure because very bright supernova will cause saturation.
Yeah, so LSST saturates at like around 17th, 18th magnitude, is that right? Something like that. So yeah, the problem is you only get, kind of 5 orders of magnitude due to saturation in the detector. So you can build your system and pick what magnitude range you're going to get, but you don't get a longer magnitude range, right? So if you're doing faint things, you can't do bright things. So one of the issues with the supernova science is to couple the things we're doing on fainter objects at higher redshifts to what we see at lower redshifts, and there you run into that. A simple way of dealing with it is actually just to do some short exposures and calibrate your system against those short exposures so you can compare the bright end calibration to the faint end calibration. That affects some of the cadence discussions we're having, and still an ongoing thing. Okay, let's go to the solar system. So here, we've discussed this a bit. You want to catalog orbital parameters, size distributions, colors, and light curves of small body populations. So clearly we're looking at time varying things. In this case, they're moving. They're also changing in brightness. But obviously, you still need a large number of observations and multiple filters. The cadence is constrained in the way we talked about earlier. You need closely spaced pairs of observations, typically 2 to 3 times per lunation, in order to link the detections. Here's where trailing comes in. Obviously, if the object is moving and you have too long an exposure, you're going to see a track rather than a point. How do you think that degrades your sensitivity for detection? But it's just a formal statistical thing. Work it out. Obviously, as I spread the light over more pixels, the signal noise per pixel is going down. But I have more pixels. You can actually show that you're going to longer exposures once the object trails doesn't actually hurt your detection sensitivity. It actually just stays constant. So going to longer exposures improves your detection sensitivity per visit until it starts trailing, and then it's flat after that and independent on the exposure length. But there's still a reason why you don't really want trailed objects in the field, because it's degrading your ability to determine their absolute position because of the signal noise per pixel. There, in that case, just detecting the object isn't effective, but measuring its position for an orbit is effective.
Really embarrassing question.
Yeah.
What is a lunation?
It's the moon goes around the sky in a month, so a lunation is effectively a month.
I guess it's something to do with the moon, but
Yeah. No, but if you go into a bar, you meet someone, you talk about lunation, that sounds cooler than talking about month. There's a lot of words in science we use for that. That's right. Yeah.
So, but if you let it streak, you get the vector without saying.
You do get a vector, but you don't get, it depends on the width and how long that trail is. I mean, for a very fast-moving thing, you get a nice line. But in practice, what you get is a fuzzy blob where the extra length is not doing much compared to the PSF, and you're hurting your position in the cross direction. So it ends up not helping you in its beam width. Yeah. Yeah.
With the streak, you must have a threshold where you have no idea what the direction is, but you just don't know what pixels to add up.
Yeah, I mean, well, then you could imagine designing a smart algorithm that examines all pixels to try to find whether possible streaks are there and does some maximum likelihood to see if they're real. But people have thought about doing things like that. So in any case, we concluded that the individual exposures should be shorter than about 30 seconds to minimize this trailing effect. Obviously, we need good image quality, astrometric accuracy, good photometry. You might wonder why we need that for the solar system, because a lot of the science there has to do with trying to understand the shapes and albedos of these small bodies. And they vary in brightness as they move along their orbit because they're rotating relative to the sun. And those kinds of variations tend to be of order a few percent. So you want to have that kind of photometry. Good sampling of the filters over time to get different colors, which again tells you something about composition and shapes of these objects. And then I actually forgot to put this plot in there. For the near-Earth objects, or the potentially hazardous asteroids, there's this issue of how faint do you need to go? And there's actually a congressional mandate that was adopted in the late 90s saying that, we needed to know all the asteroids down to 140 meters with, 90% completeness or something. Do you know how they picked 140 meters? It was actually a metric. It's what? Actually, 140 meters doesn't kill everyone. But if you go much smaller than this, something else happens.
oh, it breaks up.
Breaks up in the atmosphere.
So how big of a disaster is it if 140 meters hit? It doesn't break up, but how bad?
So what do you think is the most dangerous thing that can happen from a sort of 150-meter asteroid running into the Earth?
Congressional action.
Tsunami, yeah, it's a tsunami. And most people think about it hitting your apartment building, but the probability of hitting your apartment building is 10 to the minus 10. The most likely thing an asteroid will do is fall in the ocean. And an asteroid, this will cause a very significant tsunami.
So anything less than 140 basically explodes in the atmosphere.
Yeah, basically. And the reason why you want to know these guys is because the distribution is a power law. And so as you go to a kilometer size or bigger, yeah, those are really, really bad. Those destroy civilization, but they're extremely rare. And in fact, we actually know most of them. So it's when you get down to this range that our completeness is low right now. It's not better than about 20, 30% or so. And yet they're still bad enough. You go much smaller than this, then. So you take a 140-meter object, which is kind of in an orbit that could impact the Earth on the, say, human timescale. That gives you an idea of how far away it is. And then you can estimate how bright that object would be. And it ends up being about 24 and a half. Well, it's more precise perhaps than that calculation, but it sort of gives you a flavor for how deep do you want to go in a single visit in order to measure these things, in order to get down to that.
Regarding the training, so you got some additional information about velocity, right? Out of the trail.
That's what I was saying. So for, you know, for artificial satellites around the Earth, they look like streaks. So if they're bright enough, you'll see a very clean line. You can obviously measure its position, its velocity very well. But actually, for these asteroid things, when they trail, they go a few pixels. It gives you kind of a blob. It's not a very good vector in and of itself, and it's degraded your positional accuracy by spreading the light. It's not worth it, yeah, is the answer. You're better off coming back later and seeing the 2 points rather than trying to trail in a single exposure. Yeah.
Does this conventional mandate make sense though? Because there's not really, the relationship between size and number of photons is very variable. You could have an
Yeah.
object that's bigger than that, completely matte black, and then see it.
Yeah, so what the argument was, everything that could impact the Earth with 90% efficiency down to 140 meters, so you got to average over those distributions, and that's where this comes from. That's why you never get 100% completeness. But if your question is, was Congress thinking intelligently when they adopted this mandate? I'll give you an example. So there was actually a House Science Committee hearing on near-Earth asteroids a number of years ago, and Tony Tyson was one of the people that testified at the hearing. And the congressional mandate was that we need to find all the near-Earth asteroids, or potentially hazardous asteroids, down to 140 meters with 90% efficiency by 2020. And Tony testified that if they would build LSST, with what we've designed it to be, we would find all the 140-meter asteroids with 90% efficiency by something like 2025. And the question he got from the congressman is, what are we supposed to do for those 5 years? So that's the level of logic.
What was his answer?
He tried to answer without being insulting. Yeah. Actually, the main reason we couldn't get there by 2020 is they just didn't start the project. It's delaying the project got us, move that time out. Okay, so exploring the transient optical sky. Here, you're looking for the unknown. And so, as I said, if you don't know what timescales you're looking for or how many objects or what frequency, it's hard to be very quantitative in what you want to look for. What you try to design for is something that, is sort of maximally non-committal so that you have a chance to find lots of different things. Obviously, large area coverage to enhance probability of detection, good time sampling, accurate colors. Here, the rapid data reduction becomes a big issue because we want to broadcast that we've seen something to the community, so that puts a lot of drivers on the data management system. And then, as we talked about earlier, this cadence sampling on all timescales. This is a plot due to Sri Kulkarni, which has evolved over the years. He's been showing it for a long time. He calls it the Zwicky plot. So it's kind of how absolute bright is an object versus what is a characteristic time scale. And sort of known things fall on this plot. Novae fall here, type 1a supernovae here. These are the core collapse supernovae, luminous blue variables. The point Sri makes in showing this plot is that, in principle, things can live anywhere on this plot, and every time we look in sort of the time domain, we find things we didn't know about. So there's no particularly good reason to believe that new things, the unknown unknowns, are going to sit in any particular part of the diagram. But what you do know is there's a big white space here, which is not because there's nothing that lives there. It's just because that's where we've never looked. So if you're trying to, this is a short duration phenomenon that go faint, clearly that's kind of the hardest thing to do. So if you're going to try to think about LSST opening up the time domain, that's kind of where you want to be, and you see it's kind of on this plot. It's also about 24th magnitude per visit, and the characteristic time scales are less than a day, so the kinds of things that LSST will do. So that's why LSST is important for this science. And mapping the Milky Way, as we talked about earlier, there's actually two things we've adopted in this area. One is to determine the assembly history of the Milky Way, which is by looking at satellite galaxies as they fall into the gravitational potential of the Milky Way. As a satellite galaxy falls in, there's tidal stripping. The stars get pulled out, and they actually follow the track that the original galaxy took. So they, in some sense, show you the orbit in the dark matter potential of the galaxy. It gives you constraints on dark matter models. And then also, from a stellar physics point of view, the idea was to measure the fundamental properties of all of the stars within 300 parsecs of the sun, so we get a sort of complete sample of stars that we can see. And clearly that gives you some characteristic depth that you want to get to, which turns out to be R of about 27. Also, interestingly, very close to where the galaxies start to disappear. So this requires large area coverage of the sky because the Milky Way fills most of the sky. Excellent image quality for this photometric and astrometric accuracy. Photometric calibration better than 1%. Astrometric precision to 10 milliarc seconds. The co-added depth is 27. A lot of the stellar science depends on estimating metallicity of stars, which is an indicator of stellar age for those of you who are not astronomers. And to do that, you need things that are sensitive to features in the spectrum that come in different places. And the U-band turns out to be particularly interesting for that. That takes you to U of sort of 24.5, which is compatible with the R of 27. And then you can say, how much are stars actually going to move if I'm looking hundreds of parsecs away? And you really need to be down at the level of 0.2 milliarc seconds per year. And we want to get out to, an arc second is the distance a star moves due to parallax at 1 parsec. So if you get down to milliarc seconds, then you're going out to a kiloparsec, which is sort of the dimensions of the galaxy. So that's actually getting you out of the disk of the galaxy. And we want to be able to do that over 10 years. Yeah, I didn't bring that plot, but actually it turns out, and as far as I can tell, this is a complete accident. But it turns out that, so Gaia has a plot of astrometric accuracy as a function of magnitude, and not surprisingly, the accuracy gets worse as you go fainter. And LSST is almost an exact continuation of that line. So where LSST comes on at the bright end is right where Gaia leaves off, and where LSST at the faint end, and the line continues pretty much. So it's actually really nicely complementary between Gaia and LSST in obviously going out to much larger distances with reduced precision. So these are, so those kinds of arguments led to this overall synopsis of, what sort of constraints you want. For the reasons I showed you, you want to get to a single visit depth of about 24.5. We want the seeing to be, the image quality to be as good as we can get it, which means we choose a good site and then, don't degrade it by building a crappy telescoping camera. So the image quality is about 0.65 arc seconds. Photometric repeatability is the sort of this 1% or 0.5%. How good can you compare observations made at different times or in different colors? That's about 5 millimagnitudes. Applies to both repeatability and to comparison of different color bands. Astrometric precision of about 10 milliarc seconds per visit down to 1 milliarc second over the survey. Single visit exposure, I showed you that it can't be much longer than 30 seconds because of the trailing. And there's another argument I'll come to in a minute, but it also can't be too short. Otherwise, you get read noise limited. So if you think about, the CCDs have a few electrons of read noise, and if you do very short exposures, that starts to dominate over the Poisson fluctuations in the number of counts. So you want the observations to be what we call sky limited, and for most of the bands, that means sort of 20 seconds or so. But the other reason why this can't be too short is you're wasting time reading out the camera and slewing around and doing all that kind of stuff. The efficiency of the survey starts to get less good. The filter complement, this is a question asked earlier, why 6 filters, why not 20? And it's largely just how faint you're going to go versus how wide a band. We want to cover the whole visible spectrum because objects have spectra which cover the entire visible spectrum. You'd like to use as much of it as possible. The cadence must enable the determination of the orbits of solar system objects while also providing good sampling on all time scales for the time domain and sufficient long time coverage for parallax measurements. For example, it would be a mistake to do all 1,000 observations for one part of the sky in the first year and then move on to another part of the sky and do 1,000 observations, because you wouldn't get enough of that annual periodicity to give you very good parallax sampling, okay? So it's clearly a balance between those things. Total number of visits, 1,000. That's a somewhat arbitrary number, but it actually ends up being implied by these others, as we'll go through. Co-added survey depth, 27.5, which, as I showed you, applied to the galaxies and also applied to some of the other science. You need to ensure you have enough visits per filter to be able to get enough color information to do the photometric redshift. Sky coverage as much as you can get. Almost all the science benefits by covering as much sky as possible. Yeah, question? No, that's total. So it's about 250, 300 visits for the filters which are sampled more often. And then this issue on the processing for the follow-up observations, fast processing to enable time domain alerts in 60 seconds with annual processing to achieve full calibration accuracy. So how does this turn into, you know, what you actually build? So the next few slides go into sort of what you actually build. And clearly, one of the first things you want to figure out is what is the aperture size? And actually, let me turn this slide off. So from that consideration, what do you think would be the driving consideration on how big the telescope should be?
You mean the mirror size?
Yeah. There's two ways to get an answer, coming from very different arguments. Yeah, but that's not what we're looking at. You can build anything you want. Let's say you can build anything.
Why is it not as big as possible?
Okay, so you have an 8-ton-do requirement, which is what we need to do to get 27th magnitude over 20,000 square degrees. So here's one way of getting it. You have an 8-ton-do requirement that gives you meters squared, degrees squared. If I say I want 1,000 visits over that 20,000 square degrees, that tells me how big the camera has to be, okay? And if I have the camera field of view and I know the 8-ton-do, I get the mirror size. That's one way to get that. The other way to get it is to take the 20 to 40 seconds and say, I need to go to 24th magnitude in one visit. How big a mirror do I need? That's independent of the field of view, but it does depend on the mirror size. Okay, so both arguments give you similar numbers. Yeah?
Doesn't that just tell you the total collecting area, not the size of one mirror?
Yeah, it's the collecting area, the effective aperture size. Yeah.
So what's the argument for only doing one?
That's a very interesting question. Let me come back to that question. Yeah. Because there were people who said it's really stupid to build one. And they were wrong. But let's come back to that question later. Okay, so the aperture size, this is basically what I said. The co-added depth over 10 years for full 20,000 square degree coverage determines the system 8-ton-do. That's the 300 meters squared degrees square. 1,000 visits in 10 years tells you the field of view of the camera, 10 square degrees. The 8-ton-do and the field of view constraints gives you effective mirror size of 6.5 meters. The other way to get it is to say, I want to do an observation in 30 seconds. You know, to get to 24th magnitude, how big does the mirror have to be? And it's about the same. And I'll show you some plots of that later. And then if you don't take the exposure time as a predicate, you can turn this around and say, this is the mirror I'm going to get. I want to get to 24th magnitude. How long do I have to integrate to get there? That gives you about 30 seconds. But as we saw, there are other factors there, avoiding trailing, revisit time, number of visits, and together they yield something like exposure time less than 40 seconds. And these are just the charts sort of plotted for different aperture diameters, just so you see what you look like. So on the left here, this is the total co-added 5 sigma depth as a function of how long the survey runs for different size mirrors, okay? And this basically tells you that if you want to get to 27.5 magnitude in 10 years, then you need something like a 6.5 meter mirror. Actually, one of the questions which we sometimes get, why 10 years? Anybody have an answer? Why is 10 years the right number for the survey?
Things advance so quickly that you don't want to build something that's designed to run much longer because the thing that's being built 10 years from
Yeah,
now will do so much.
that's actually the right answer. There's two right answers. One, that the technology goes obsolete, the camera in particular. And two, because people get bored. And three, because you can't run it much shorter than 10 years or you don't sample the parallax or some of these timescale phenomena that we want to get to. So 10 years ends up being kind of a good number for human reasons. So then the chart on the right is that this is the single visit depth. Remember, we're trying to get to 24.5, as opposed to how many days is it before you get back to the same part of the sky. Now, the number of days before you get back to the same part of the sky obviously depends on the duration of the exposures or the visit duration, because if I'm taking very long exposures and I still want to cover 20,000 square degrees of sky, then it's going to take me longer to get back. So this could be a proxy for the exposure duration. There are clearly simple algebraic relations connecting those. And if you say I want to get to R of 24.5, and some of the science arguments say you want to get back within a few days, for example, for supernovae, for asteroids, for other things, then that also gives you a mirror for LSST, which is 6.5 meters in diameter. So
Is that back in the same band or back to the same side?
actually, it depends what you're doing. So for the supernovae, actually, you would like to get all of the colors except you. For the asteroids, there are arguments about whether you need to be back in the same color or not. And for the orbit determination, the answer is probably no, you don't. But if you want to study things like the albedo, the rotation, et cetera, and you're changing the color all the time, that makes it worse. The interesting thing is that these numbers didn't have to work. It's not given that all these things converge on the same numbers. If they hadn't converged on the same numbers, LSST would be doing what PTF is doing now, which is to say I cannot do a single survey that meets all these signs. So for the first 6 months, I'll do a survey that has this cadence, and the second 6 months, I'll do something else. If we were constrained to what we could build, and these numbers didn't work, we would have to work that way. It was actually the genius of Tony Tyson, even in the late 90s, to realize that these kinds of back-of-the-envelope calculations converged on roughly the same parameters coming from very different angles, and that was not obvious at all before that. Yeah, so that was the question that was asked over here. So, you could say, well, why not build a bigger mirror? You don't have, what I've shown you is you don't need to build. There's no particular advantage in building a bigger mirror, but you could. And the answer is yes. The LSST design was thought to be, am I getting close to the end of time? Okay. You going to allow me to go over, or should I try to skip through? All right. So there's sort of a limit on the size of a monolithic mirror that you can make, which is, there's a very practical limit in that with this particular technology, the ovens, the rotating ovens at the U of A can only do 8 meter mirrors. I can't do anything bigger than that. But also, when you try to do bigger mirrors than that, there are sort of mechanical engineering issues. So it's not surprising that around the biggest telescopes in the world with monolithic primary mirrors are all around 8 meters. Keck is a segmented mirror. For the 30-meter telescope, that's a segmented mirror. For the Giant Magellan telescope, which will get to 20 meters, that's a set of, 7 8-meter mirrors working together. So the single monolithic mirror size is not going bigger than 8 mirrors with anybody's technology. So that is kind of a practical limit. These are the filter bands. I think most of you have probably seen this before. The interesting design issue here, which I won't talk about because we don't have time, is just not so much where the bands are, but what should be the steepness of the edges of these filter bands. And you can imagine, why wouldn't I want those filter bands to have very sharp edges to be cleanly discriminating one from another? And the reason is we're not entirely sure we can get that wavelength band to be uniform across the whole filter. So if you have variations in the filter band as a function of position in the filter, then for different objects you could open up gaps. And gaps in the filter bands are bad because there's a region then in redshift space where you really have no constraint. So you always want to get some overlap, and the way you get overlap is to sort of make these tapered so that they cross, and then you can afford to slide each one a little bit to the left and right and still get enough overlap. So that was something we did a lot of studies on with LSST. So this is the summary of the high-level requirements. I've shown this slide a lot, so most of you have probably seen it before. And this is just sort of a quick, in a nutshell, how do you go from those kinds of parameters to what the thing actually looks like. So the median delivered seeing at the site is 0.6 arc seconds. And the usual rule is you should sample your resolution kernel at least 3 times. In sort of noise information theory, that means that the plate scale should be 0.2 arc seconds per pixel. So that's what I meant earlier. You don't really have a choice on the plate scale. That's kind of given to you by the atmosphere. But you can adjust the pixels to fit that. That can be 0.2 arc seconds is the size of a pixel in angular space, not necessarily in physical space. But you can very quickly convince yourself that with this 10 square degree field of view, we're going to have a very large camera. That's costly. So you're going to want to make the camera as small as you can conceivably make it. And there's a limit on how small you can make the pixel size, which maybe Chris covered this morning, associated with charge diffusion, right? Because we have these deeply depleted devices, the charge is diffusing. Forget about the asymmetries, even just the regular thing. If the pixels go too small, you're not really utilizing that resolution. That turns out to be about 10 microns or so. And so this is kind of the smallest you can make the pixels, which is what you want. You're going to match that to 0.2 arc seconds. That gives you a plate scale. Okay? Once you have a plate scale, then that determines the focal length, right? Because the focal length gives you the plate scale. The focal length is 10.3 meters. We argued earlier that the minimum aperture diameter is about 6.5 meters. This is if you had no hole in the middle, just a single structure. And that tells you that the focal ratio, which is the ratio of the focal length to the aperture, the diameter of the aperture, is less than 1.5. It's an F number less than 1.5, which is a very fast optical system and creates all kinds of problems. In actual fact, for LSST, the real F number is 1.2. It's even faster than that. And the number of required visits tells us the field of view, which is 10 square degrees, or about 3.5 degrees in diameter. That, coupled with 0.2 arc seconds per pixel, tells you how many pixels you need. So that's where the 3.2 gigapixels comes from with LSST, just from these simple considerations. And then the number of pixels and the physical size per pixel tells you how big the focal plane is, and that's the 63 centimeters. So there's really not a lot of way to get away from this logic, okay? The only way you could go away from this logic is to make an even bigger camera, right, which would be more expensive, et cetera. And then the telescope mount, the main issues in designing that are to keep it compact so that we can slew it around the sky as fast as possible. And here's an interesting slide. This is what the optical design for LSST looks like. And the light comes in and bounces off a primary, which is an annulus. So this is what Phil was referring to earlier. There's a big hole in the primary here. That hole is filled, so light comes in, comes off an annulus. So actually, the real physical diameter here is 8.4 meters, but the effective diameter is 6.5 meters because of that hole. Then it goes off a convex secondary on into a tertiary, and then finally on into the camera. Does anyone know why there have to be 3 reflections? Actually, every wide field telescope that anybody's designing nowadays has 3 reflections. Yeah, it's because normally with a primary camera where you have just the primary going in, you can adjust the figure to take out coma, which is the first effect that has. But if you want to get out to a field of view that's like 10 square degrees, you have to cancel coma and astigmatism. And you can't do that with less than 3 bounces. So it's because you're trying to cover both of those things that you need the 3 bounces. In fact, You could actually, just with the 3 bounces, make an astigmatic, aberration-free field without any lenses at all. But there's a reason we need these lenses. Anyone other than Aaron know why we need those lenses? You could, without these lenses, you could make a flat focal plane just by adjusting the surfaces of those mirrors. That's not the problem. If we were doing this with film, we could get away with no lenses. The problem is we're trying to do it with electronic detectors. We have to keep them cool. The only way to keep them cool is to put them in a vacuum. If you put them in a vacuum, you have to have an entrance window to the vacuum. And if you put an entrance window in this, forget about the lenses, what happens? You generate chromatic aberrations because the light of different colors reflects a different way, and it's now in a converging beam, so the images in different colors start to move apart. So because we have to put that window in there, we have to take out the chromatic aberrations that would otherwise occur, and that's what these lenses are doing. So it's L1, L2, and L3. They don't have a lot of optical power. Their main effect is to make it such that with those 3 refractions, you basically end up in the same place with all the different colors. This is what the mirror looks like. You've seen this. I won't say much about it. This is what the telescope looks like. This telescope, the building for this telescope is highly asymmetric. Anyone know why that is? Yeah, it's because the wind comes in this direction. So what you really want to do is put all the services, the heat dissipation in the building downstream from where the telescope is, so the telescope environment is pristine. And the wind mostly comes that way. So it actually looks like an ocean liner because it's the same reason ocean liners are designed that way. The telescope is very stiff and stout. The reason for that is to raise the fundamental frequencies to pretty high levels. They're of order 8 hertz or so. You want to keep the telescope from wobbling around as you move it around different parts of the sky. There's a lot of constraints on the camera. I'm running out of time. Maybe I won't just, these are sort of obvious, so I'll go through it quickly. You have a very large field of view. You can't build very large CCDs, much larger than, that. So you're obviously going to have a large number of CCDs, and you've got to space them all close together. This very fast beam, f1.2, means that the depth of focus, or the depth of focus is very short. So this is the same thing on your SLR camera. If you open up the f-stop to the lowest number, you know that you have a very short depth of focus. And the only way to get around that is to make the focal plane all very uniformly flat. Otherwise, you're moving different parts of the field in different focus. The camera's sitting in the telescope beam, so we don't have a lot of room there. That puts a lot of mechanical constraints on its design. Broad spectral coverage require these deep, fully depleted CCDs that Chris talked about. We're taking short exposures, so we need fast readout. Otherwise, we're spending most of the time with the shutter closed. And that requires reading out 3 billion pixels in something like 2 seconds. There's a maximum speed at which you can read out a CCD before the read noise goes to hell. So the only way you can fix that is to massively parallelize the whole system. And we divide each of the CCDs into 16 readout amplifiers and bring it all out in parallel. That leads to a huge number of signal lines and a large cryostat. And that's driven us to incorporate the electronics directly in the cryostat, which is a messy, complicated design that people haven't really done before. And it introduces all sorts of issues about contamination control and everything else that we're working on. But this was the argument for it. That's what the camera looks like. You've all seen what the focal plane looks like. Each one of these blue squares is a 4K by 4K CCD. And the red squares are what we call RAFs, which are arrays of 3 by 3 sensors. I'm not going to say much about the data management system. This is basically what we've decided we need to deliver. This time domain stream within 60 seconds, annual processing, and then there'll, of course, be a lot of software produced by the community to do all these great analyses. Yeah, these numbers are from Mario Juric, who is the only person, I believe, actually. So Mario will be here tomorrow, and you can probe him directly.
Even previously, although it said a million on your slide, you said 5 billion.
No, there's a difference between how many objects you detect and how many you can use for lensing. So we talk about 20 billion galaxies, but of order 4 billion in the so-called gold sample, which are well enough measured that you have. That's where that difference comes from. You might worry about computing resources. These are very old slides. They show sort of what the CPU requirements are as a function of time, although the horizontal scale is off because we assume that the project was starting earlier. And this is what the top 500 look like. I was going to say something about simulations. I'll leave that out. Let me just say something about cadence optimization, because this is the one part of the design which is actually still not fixed. We're building the hardware, and we pretty much know what that has to look like. But once you've got the telescoping camera, you can move it around the sky in different ways. So the cadence is not really governed by any real constraints, and therefore doesn't need to be decided until we actually start doing the survey. But there are some issues with just the whole question of how you're going to schedule this thing, because we're obviously going to need a software that schedules LSST. There's not going to be a human every 30 seconds deciding, okay, point here. And the logic that goes into that scheduler is kind of an interesting question. It's actually a real traveling salesman problem. It's worse than a traveling salesman problem because all the salesman cared about is how much he was driving. Here we care about more complex things than just how far have I moved. We care about, did I get enough sampling on various different times? Did I get the filter choices? So it's known that a traveling salesman problem is not solvable, and this is sort of n times not solvable. Okay, so it's a question of what is the optimization that you'd actually do, and we're sort of still studying that. And there's trade-offs for reasons I went into. The dumbest thing you can imagine doing is evenly spacing your 1,000 observations over the 10 years. That doesn't give you very good sampling for fast things. But if you, as I mentioned, if you put all your fast things in one part of the sky together and then went to another part of the sky, you'd lose the longer timescales. So the way we've gone about this is to try to get the community to write metrics for if we gave you 10 years of observations, what the times are, where you were in the sky, what the observing conditions are, you could say, that thing rated a 7.9 on my scale for my particular science, and if I gave you a different set of 10 years of observations, you'd say it was a 6.3. And then if we could put those quantitative metrics together and figure out how to normalize them with respect to one another, and Phil has suggested ideas about how you might normalize them, then maybe we could globally optimize something that was good for everybody's science. That's what we're heading to. We're not there yet. I don't think I'll talk about this. This repeats some of the other stuff. The main religion here is to try to keep it true that we're only doing one survey. And so we want to try to accomplish all this different science at the same time. As I showed you earlier, it's remarkable that it actually does come together as well as it does. But it's not perfect. And clearly some ways of operating would be better for some science and worse for others. And that's what we're trying to figure out. There are some constraints on how you can operate the survey for basically the dumbest of all possible reasons. We can only actually put 5 filters in the camera at any one time, not 6. And the dumb reason is that only 5 fit. And you might think you just designed it badly, but when you look at the constraints of how big the camera can be in diameter, you can only fit 5, period. That's the way it is. So there's a 6th filter, which you can move in for any one of the others during the day and then do a few nights with a different complement of 5 filters, and that's the way we operate. There are limits on exposure frequency due to thermal considerations. If you try to run the camera very frequently, you're changing the thermal behavior. That doesn't break the camera, we don't think, but it may change the calibration, so that has to be thought about. There's a lower limit on the exposure duration, which has to do with the way the shutter works. The assumption has been 1 second, but we're currently evaluating that. And there are obviously limits on elevation in both directions. You don't want to go too low because you're looking through too much sky, and you don't want to look at the zenith because you can't track in any way. So there's a limit in elevation. Science-related constraints. We've decided that weak lensing, which depends on image quality the most sensitively, will be done in the R and the I bands, so you want to go to them preferentially when you have anomalously good seeing. The Z and the Y bands, the infrared bands, are less sensitive to bright time and twilight, so you want to use that time in those bands. U band can only be done during dark time, and so therefore it is most often the 6th filter, which is sitting outside the camera. We put it in during dark nights. Repeat visit to each field on timescales less than an hour. This is for the moving objects I talked about earlier. And you want to dither the field centers to reduce exposure variations on the sky. If you imagine that you always go back to the same center every time you come back to that part of the sky, what you find are there is overlap regions which are really very well sampled, and then the regions between the overlaps are less poorly sampled, so it's imprinting on the spatial distribution on the sky a very strong window function which will reverberate in the correlation analyses for things like large-scale structure and for weak lensing. Yeah, it's because we get the highest depth in the R band. It has less atmospheric dispersion than the G band, for example, and you go fainter than you do in the infrared bands. So we think right now that the weak lensing analyses will probably primarily utilize R and I bands. You can only do that in dark time because the sky brightness kills you otherwise. Yeah. So these are some guiding principles: maximize efficiency, be flexible to discoveries. However, one of the key things, people might think like, oh, in year 3 of LSST, let's sort of give up weak lensing because cosmology is boring. We already know W equals -1. We argued that the whole point of building this is that some of the science really takes 10 years. So we're going to have to exercise some discipline so as not to abandon our science a few years into the survey, but obviously have some additional flexibility. And obviously the community will have to be involved in that. And so this is what I talked about earlier with these metrics. I won't go into that. And then just a summary. So the LSST design was strongly driven by the 4 main science themes. It is still remarkable to me that we can meet most of our requirements with a single survey. So that's what we call this massively parallel astrophysics. There's a lot of optimization left to be done, but it's primarily in this cadence thing and the time sampling. So I'll stop there. Sorry for running over.
It's okay. Do you have to head off somewhere else this afternoon?
Let me look.
We're having coffee at 3:30 if you want to come and hang
Okay. All right. Let me just see what I have.
out. Okay. So while Jim's setting up for his talk, you might want to stand up, move around a little bit.